This is AP Chemistry, Chapter 5.7, Enthalpies of Formation. So there are a lot of different ways to calculate change in enthalpy, and there are a lot of different enthalpy values, but the one we're going to be focused on is the enthalpies of formation. The enthalpies of formation means the formation of a compound from its constituent elements, which is each element that goes into the compound. By finding the enthalpy of formation of the reactants and the products, we can calculate the overall enthalpy change of a reaction using Hess's law. If you don't already know, Hess's law says that if a reaction is carried out in a series of steps, the change in enthalpy for the entire reaction is going to be the sum of the enthalpy changes during each step of that reaction. The magnitude of any enthalpy change is going to depend on the temperature, the pressure, and the state of the reactants and the products. And by state, I mean whether or not it's a liquid, a gas, or a solid. Since all of these different factors can have an effect on the value of the change in enthalpy, we're going to want to define a set of conditions, which is where standard state comes in. The standard state of any element is a substance's pure form at atmospheric pressure, which is 1 atm, and the temperature of interest, which is usually 298 Kelvin, which is 25 degrees Celsius. By using the standard state and keeping things similar by defining a constant, we can compare the enthalpy changes between different reactions. The standard enthalpy change of a reaction is the enthalpy change when all the reactants and the products are all in their standard states. When we put that all together with the enthalpy of formation, we get the standard enthalpy of formation. The standard enthalpy of formation is the change in enthalpy for the reaction that forms 1 mole of the compound from its elements when all substances are in their standard states. We usually report the change in standard enthalpy of formation values at 298 Kelvin, but if an element exists in more than one form under standard conditions, we're going to want to use the most stable form. These equations always show that 1 mole of the desired substance is being produced. There's 1 mole of the product. So the standard enthalpies of formation are reported in kilojoules per mole of the substance that's being formed. For example, here's the standard enthalpy of formation for ethanol. Now, when we look at this, we're going to notice that the elemental source that we're using for oxygen is O2 instead of just one oxygen or O3, since O2 is the most stable form of oxygen when it's at 298 Kelvin and 1 atmospheric pressure. We're also going to see that the elemental source we're using for carbon is graphite instead of something like diamond, since graphite is the more stable form. It has less energy. It's the lower energy form at standard conditions. Then we're also using H2, hydrogen gas, because this is also the most stable form of hydrogen. And as we can see, 1 mole of ethanol is always produced because we always produce 1 mole of the product. So the change in standard enthalpy of formation of the most stable form of any element is going to be 0, because if you think about it, you don't need a formation reaction when the element is already in its most stable form. So there's no reaction that's going on, so there's no change in enthalpy. Now that we understand this, we know that the values of standard enthalpy of formation for graphite, hydrogen gas, and oxygen gas are going to be 0. We can break down any reaction into the formation reactions. By doing so, we obtain this equation. This means that the standard enthalpy change of a reaction is the sum of the standard enthalpies of formation of the products minus the standard enthalpies of formation of the reactants. This will be the equation that we're using to find the standard enthalpies of formation for different reactions. Now let's go ahead and try sample exercise 5.11. Calculate the standard enthalpy change for the combustion of 1 mole of benzene to carbon dioxide gas and water. So we know that a combustion reaction involves oxygen and something else, so this reaction is going to involve oxygen gas. Now that we have the full equation written out, we have to balance it too. Since we can only have 1 mole of benzene, we can't keep going and changing things so that we can have an even number of oxygen. So we're just going to have to put a fraction. Now we're going to go ahead and use our appendix C to find the standard enthalpy of formation values. Always make sure that you're recording the correct value for the state, because sometimes there will be more than one state for the same exact compound. Since we're already using the most stable form of oxygen, the standard enthalpy of formation is going to be 0. And go ahead and finish filling in all the standard enthalpy of formation values for your product side as well. If we remember our equation that we used earlier, we can go ahead and rearrange our products and our reactants so that we can solve for the standard enthalpy of our reaction. Solving both sides separately and then subtracting them makes it a lot easier to get your final product. The standard enthalpy of this reaction is negative 3,267.49 kilojoules per mole. For part B, we're supposed to compare the quantity of heat produced by the combustion of 1 gram of propane with that produced of 1 gram of benzene. Thankfully, the book already gives us the standard enthalpy of the combustion of 1 gram of propane, which is negative 2,220 kilojoules per mole. Since we're going to need to do a mole to gram conversion, we're going to have to use our periodic table to figure out the gram per mole of propane, and then use that to get the kilojoules per gram of propane. So right there I actually made a little mistake, but we're just going to pretend that never happened. For the second part of this question, we're just going to use the negative 3,267 kilojoules per mole that we got from earlier. And just like for propane, we're going to have to use the molar to gram conversion with benzene. Now that we have finished our equations, we can see that the reaction for propane gives off more kilojoules per gram than the reaction of benzene. Now it's your turn. Go ahead and pause the video here and unpause when you're ready for the answer. This problem is probably going to be a little bit harder, but do the same for the last one and pause here and unpause when you're ready for the answer.